electricity and magnetism. Remember the time I took the rubber rod and I charged it up? Okay. Well, pretend this is the rubber rod charged up. And now I shake it through space. When I shake it back and forth, is that not an electric current? Charge in motion? What surrounds an electric current? Begin with MF. Magnetic field. How many say, oh, that magnetic field is probably very, very steady? How many say, no, the magnetic field changing. What's a changing magnetic field induced? Begin with EF. Electric field. What's a changing electric field induced? Begin with MF. How many starting to catch on? What does the changing magnetic field induce? Begin with EF. What does the changing electric field induce? Begin with an MF. How many getting the idea? Okay. It turns out these waves will regenerate one another. So if you have a shaking charge, honey, you get electromagnetic waves throughout space. Where the electric field makes the electric magnetic at the speed of light. That's what light is. That's what light is. Light is electromagnetic waves generated from a shaking charge. If I take this stick and I put it in the water and I shake it back and forth, won't I disturb the water? Won't water waves travel out? You can understand that. But what I'm saying is you take a charged object, or just take a charge, shake it back and forth, and guess what you generate, gang? Begin with a W. Waves. And these waves are electric and magnetic fields, so guess what kind of wave? Electromagnetic wave, that's right. And that's what we're going to talk about now. Electromagnetic waves and the very, very small part of the electromagnetic waves. You get the whole spectrum of waves that start way down with the radio waves, really long, long waves. And the radio and the frequencies get a little higher, and pretty soon those waves, for example, your radio antennas downtown are shaking waves up and down like a few million times per second. That's your FM waves. A few thousand times per second, that's your AM waves. But if you shook the electrons in your radio antenna up and down like a million billion cycles per second, honey, the waves that are generated are going to activate what? Begin with EY, get an E on the end of it.
I.
Your eye, that's right. Remember we had the tuning forks that time? I hit one tuning fork and made the other one ring? Well, in your eye, you've got tuning forks there too, and guess what frequency they ring at, gang? Million billion cycles per second. Million billion hertz. And that's light. And light, when that light comes in your eye, it makes, that's sight. Would you like a profound statement for a party sometime? When you want to say something and everyone will say, wow, heavy, man, heavy. Would you like that? Would you like to hear one? Yeah. Here it is. You probably will want to put this in your notes. Here it is. Light is the only thing one can see. There's a lot of substance to that, huh? Would you like another one? Yeah. Just as good? Sound is the only thing that one can hear. You'll have people following you after that, right? Say, hey, this dude is heavy, okay? You get the idea. Anyway, we got all these waves, gang, and a little narrow band of those waves. Starting off with the low frequencies that look to the eye to be a color. Guess what the color be for the lowest frequency? Begin with an R, end with a D, try it. Red. Excellent, red. And then I'll shake it a little bit more, and guess what the frequency is? Orange. Orange. Okay, some people. Shake it a little bit more, what color are you going to get? Yellow. A little more. Green. More. Blue. More. Violet. More.
Violet.
You can't be seeing. You can't be seeing it, okay? It's not light anymore. We call it beyond the light. We don't say beyond. Someone say, what is beyond the violet? We don't say beyond the violet. What do we say, gang? Ultraviolet, okay? And those waves you don't see. And then they even go further still, higher frequencies like X-rays. When X-rays were discovered, it wasn't known what they were, so guess what they called them? No, not Y, not Z, but what? And it turned out, lo and behold, X-rays are high-frequency electromagnetic radiation. And then beyond the X-rays, you get what's called gamma rays. But that whole mishmash of waves, okay? Less than 1% we can see, and we call that light. Here, gang, I have a prism, all right? This is a prism brought in by Roger, okay? This is a Roger prism, all right? And this prism will also take the light and bend it into a rainbow. Later, we're going to take some white light, shine in here, and boom, you're going to see on the other side what? Begin with R, end with B. A rainbow, and that rainbow is another word for spectrum of colors, yeah? And this will give a spectrum of colors too. It turns out it'll give a spectrum of colors because it turns out different colors of light will travel at different speeds through this material or any material. Did you guys know the speed of light is less in glass and water than it is in air? And how come the light slows down when it gets to the glass or when it gets to the water or anything? And here's another thing. This used to bother me years ago. If the light slows down when it gets on the glass, how does it speed up when it comes out the other side? It seems if you want to get light to slow down, get on a piece of glass plates, and at the end you can just catch it in a bucket. Keep dribbling down, yeah? But how does the light speed up again? How does light get through glass? Let me give you a little scenario of something like how that works. Light is a throbbing spark of electromagnetic energy, huh? And that throbbing spark of electromagnetic energy has a certain frequency, at which it throbs, yeah? And when that whoom, hits into a piece of glass, that glass got any atoms in there? How many say, oh no, the glass probably don't have any atoms. Come on, the glass got atoms. And what's the atom have around its nucleus? Begin with E.
Electrons.
Electrons. And guess what those electrons will do when that electromagnetic energy hits them like this? Hit, boom, they'll start moving the same way. They'll be set into vibration, okay? Now, what's a vibrating electron do? Did we talk about that before? What's a vibrating electron do? What does it emit? An electromagnetic wave. So that light will be captured by the atom. And then, boom, the atom will vibrate and, boom, send out its own light wave. That catches the next atom. When that light wave hits that atom, what's that atom do? How many say, oh, it probably don't vibrate? Come on, that vibrates too. All right, so boom, it's absorbed. Now, what's the vibrating atom do? Boom, spit. Burp, bam, bam, bam. It cascades. When it gets to the end, here's your piece of glass like this, yeah? Here's your first atom just sitting there like that. Here comes the wave. Whoop, boom, okay. Hip, I spit. Next atom, boom, okay. Boom. Hit, boom. Here's the atom right on the edge over here. Whip, boom. This one, hit, boom. And then, boom, free space. How fast did it throw it out? Free space. You know what the speed of the light was in between atoms? 300,000 kilometers per second. The speed of light that you get in a vacuum. Because guess, we think of a vacuum as void, right? Take a piece of glass, take a piece of water. What's in between the atoms? How many say airspace? No. No airspace. What's in between there, gang? Begin with a V. End with oid. Try it. A void. And guess how fast that light wave goes, or that light particle, or that light goes in between atoms? The same as it goes outside. How come light slows down when it goes through? I wonder there could be maybe a time delay between being absorbed and spitting it out. If there is a time delay, wouldn't that, in effect, slow down the light getting through? Let's suppose I have like a little toy soldier that can walk like this. And the toy soldier walks at only one speed, only capable of one speed. Okay? Let's suppose that toy soldier walks over and touches another one. And the other one starts walking. Stops. See what I'm saying? The toy soldier that comes out the end here is not the toy soldier that went in. You see that? A little time delay. If there's a lot of interactions, does that mean a lot of time delays? That means a color of light that would interact a lot ought to move slower than a color of light that doesn't interact so much. Does that make sense? Okay. And guess what color of light interacts a lot with glass? Violet or red?
Violet.
You don't be knowing that yet. Let me tell you something. The resonant frequency of the electrons in there are like ultraviolet. And when ultraviolet light comes in, and when that sets that electron into moving, boom, it is really moving. So much it bangs into everything else. And the energy degenerates into, begin with a H, end with a T. Try it. Heat. And all that ultraviolet light going to do, honey, is heat up that glass. Because it's hitting that resonance. Resonance, the vibration is too much. So the resonant won't get through. But what's below that ultraviolet? Begin with a V. Violet. And that violet's close to the resonance. And the vibrations aren't enough that they degenerate into heat, but enough to interact here, all the way by the time you... I think violet light going to take a long time to get through. Red is way, way, way down underneath. You can kind of look at it like this. Most of your atoms won't even do a darn thing when red comes by. So red just, whoom, skates right out by and only interacts here and there. Guess which color should get through fastest? You see it's red? And we're going to learn later on that when the different speeds will bend different amounts, and that's why this and the rainbows you see above you display the colors that we see. It has to do with different colors bending. And we'll know why they bend differently, because they got different speeds in the medium, different average speeds. The sun beats down, emits light. Why does the sun emit light? Honey, those electrons in that sun are shaking like crazy. All kinds of frequencies, okay? And so what you get is all kinds of frequencies of light coming down to us. And if we made a graph of the frequencies of light versus the brightness, we'd get something like this. We'd get something like this. Over here you can't even see. That's the infrared. Over here you can't see. That's the ultraviolet. But it turns out that right in here, that's the frequency of light that is emitted mostly by the sun. And that's right in the middle of our color spectrum. Because we start down here with red, orange, yellow, green, blue, violet. And guess what's right in the middle, gang? Begin with a G, end with an een. Try it. Excellent. All right. Green. It's green. Green's right in the middle. Turns out a yellow-green. A yellow-green is what the sun emits mostly. It's like a chartreuse. When I was a teenager, honeys, I had a chartreuse convertible. You could see that thing 15 miles down the road, okay? And you know why you could see it so well? Because most of the light from the sun is that color. And guess what we have evolved to see best of all? Take a guess. Yellow-green. We used to call it chartreuse.
So they paint fire trucks that color these days?
Did you notice that, Paul? What are the new fire trucks? They used to be red. What are the new ones?
Yellow-green.
Yellow-green. Why they be yellow-green, honeys? Huh? Why? Because you want to see those things coming down the road. And so they finally said, hey, let's paint them the color that human beings can see the most. Yeah. You notice the color of your street lights? What color they be, gang? Yellow. Little greenish, little yellow-greenish, mostly yellow, right? Why the street lights yellow? They used to be incandescent lamps that used to glow white. Now they're making them yellow. One strong reason has to do with, guess what we can see most? Let's suppose you got a 100-watt lamp, and it's white. And you're seeing that a lot of this is coming out, and a lot of this too, right? So you're spreading it along all that, right? Let's suppose you got 100 watts only of this. How about your eye, honey? You're going to see more light because it's hitting right where you can see best. Now, those yellow lamps aren't very good for your complexion and that sort of thing, all right? But when you're driving at nighttime, you're not into that. You're into what's on the road. You really want to maximize seeing. And hence, that's one strong reason for the yellow-green lamps and the yellow-green fire trucks. But suffice to say, we could break this up into 3 regions. That's what happens in your eye. The low frequencies average out to be red. The high frequencies average out to be blue. Guess what the middle frequencies average out to be?
Green.
Irish. What is it? Well, try it. Green. Very good. When you're looking at your television set at home, gang, you've only got 3 colors of phosphorus that give you all that spectrum of color. And what are those colors, gang? Red, green, and blue. And I can kind of show you that over here with this light box. You want to be seeing such a thing? Let's try this. Can we, Ted? All right, gang, what color is that? Begin with a B.
Blue.
How many don't even need the hint? Hey, but you guys are calling that blue, right? Can we be sure that everyone's seeing that color? Didn't you used to wonder that when you were a kid? When Daddy said, that's blue! And you wondered, your sister called it blue too, didn't she? But how do you know that she wasn't looking at this and she learned to call that blue? Do you ever wonder about that? Do we all see the same? Do we all taste the same? Do we all smell the same? Do we all feel the same? Differences, individual differences, huh? And how would you know? And look what we got here, gang. Red, green, blue, all together give what? Begin with a W.
White.
White. And isn't that nice? Isn't that nice? Because now what you're doing is the low frequency part of the spectrum, right here, banging into your eye. The middle part of the spectrum, whip, boom, banging right into your eye. And the high part of the spectrum, and it all averages out to be the white. Isn't that neat? There's another thing, too, that's kind of neat. Notice that the blue and the green mix together to give bluish green. Isn't that wild? Huh? Isn't that wild? Huh? Huh? And notice that the red and the blue mix together to give a bluish red. Isn't that wild? No, that's not really wild. You would expect that. But how about this? The red and the green, where they overlap, they give yellow.
Wow.
HC. Why should they give yellow? Now, if you mix red and green paint, you get like brown. Okay? But that's color by subtraction. Read the chapter on that. Here we have light on top of light, and red and green hitting your eye at the same time going to give you what? Yellow. Why?
Additive primary.
That's right. Yellow's right between the two, and these are going to average out to be that. Okay? Isn't that nice? Isn't that neat, gang? Anyway, yellow is oh, look at this. We talk about three colors: red, green, and blue, adding to give white. Is there such a thing as two colors adding together to give white? Answer end with a P.
Yep.
No. Yep.
Try it.
No. Nope.
No, not a PE, just a P.
Yep.
Yep. Okay. It turns out two colors can give white. Can anyone tell me what color mixed with blue will give white?
Yellow.
Yellow. You see it?
Yeah.
How many can't reason this? Well, the yellow is the red and the green. Huh? Okay. Well, let me ask this. What color, red and what color will equal white?
Cyan.
This color here, greenish blue. We don't call it greenish blue. We call it what? Begin with a C. Cyan. That's right. And how about this? Magenta, we call it. Magenta and what give white?
Green.
Green. That's right. Here's an interesting thing. Can you do algebra? White, take away red, equals what?
3.
White, take away red,
Cyan.
give cyan. Shall I do that again?
Yeah.
There's your white. Now I'm going to take the red away from it. Watch where my finger is. I take the red away. Whoops. And what's it turn into? Cyan.
Oh.
Did you ever wonder why the seawater is a cyan color?
It's green and blue.
How many people have never wondered that? So, well, hell, man, it's a cyan. Dig it, man. No. There's a reason why it happened to be a cyan. Can we have the lights, please, Ted?
Because those colors go down the deepest.
It turns out that seawater, any kind of water, absorbs like mad infrared. In fact, if you take an infrared light and shine it on water, it'll heat up very, very quickly. And it also absorbs a lot of red. So when the sunlight comes down, all the colors, yeah, hits the water, guess what color gets absorbed more than any other?
Red.
No. No, not green. Okay. Let's try. Let me give you a hint then. Begins with R, ends with D.
That's what we said. Red.
Yeah, red. Good. Okay, some people say green. Okay. It turns out the red gets absorbed. When the red gets absorbed, is that the stuff that reflects to your eye? No, it's been absorbed. You can't absorb and reflect. You take your pick, honey. So if the red gets absorbed, what does the white light become?
Green and blue.
Shall I do it again? Shall we put the lights off and do it again?
Yep.
No, I'm not going to do it again. It turns out to be that cyan color. See? If red plus cyan equal white, your problem is, what's white take away red? And that's why the seawater is the color A. Huh? Ain't that nice? That's why seawater is that color. Different colors of water, different temperatures of water, different nutrients in the water, then different shades of that cyan too, right? Having a lot to do with different amounts of red being absorbed. So the color you see in things around you are not the colors that are being resonated off. They're the colors that's a leftover of colors being absorbed. See this green, this cyan shirt here? Guess what color is being absorbed by that? Begin with the R. Red, okay? Now, we're someone with a... See this red over here, this red shirt? Guess what color is being absorbed? Begin with a C. Cyan. All right, we get... Could you do it without the hints? Well, no, okay? You get the idea, yeah? Isn't that kind of neat? Colors, fascinating. Red lamp. What color is the shadow? Black. Why is it black? Because there's no light there. Is that mysterious? How many say, wow, far out, man. Where the shadow is, it's black. We all see it's black, yeah? All right. Now I'm going to put on the green lamp. The green lamp. What's the color we getting on the background? Well, the green's a little closer. But strain your eyes. Begin with a Y. Yellow. Now I put my hand. Boom. Hey, this was the black shadow before. Now it's green. How it turned green? There's no reason for that. It just happened to turn green. I don't know why when the green light hit the black shadow it turned green. Why did it turn green, gang? Because the green light's shining on it, but the green light's making a shadow too. This one over here. But it ain't black. It's red. Why is it red? Because the red light's shining on it. How many say that's mysterious? Nobody. Come on, Ted. You see that? Ain't that neat? Now watch this. Would you like to see 3 lamps at one time? I can show you. Blue. Now what color we get for the screen? White. Bam! Hey. Now the one that was green before, now it's green. It ain't green anymore. Now it's greenish blue. Why is this one greenish blue? Because green and blue light are hitting the black shadow. Mystery? All right. Now this one over here, it's not red anymore. It's red now. But the red light's hitting, and not only the red light hitting, but the blue light's hitting it. So what is it? Reddish blue. Is it a mystery why the shadow is reddish blue? No, because the only lights hitting it are red and blue. Magenta. You get? Where some of you are sitting, you can't see it. And look over there. What color shadow we get in the far left? Why is it yellow? It ought to be black because it's this shadow here. But the green and the red are hitting it. And when red and green hit the black shadow, they whoop, mishmash to be what? Yellow. Ain't that nice? And there's your yellow, magenta, and cyan. These are your complementary colors, gang. Red, green, and blue in the complementary colors. Yellow, red, and cyan. Isn't that nice? Ain't that nice? You like? You get like a hey. If you get the right shade of blue and orange, let's try this. Let's catch that light again, Ted. Here's sort of like a sky blue, and here's like a sunset orange. And these two are complementary. That particular shade of blue and that particular shade of orange give a white, okay? It's, now, let me ask you a question. If I take that blue away from the white, what will the white turn?
Orange.
Orange. Isn't that neat? Look at that. Let's try it again. Okay. White, take away the blue, turns orange. Can you remember that? How about if it was the other way? What if I said, white, take away orange, turns blue? Remarkable? Well, the effects of that are kind of nice. Ted, the lights, please. You ever be wondering why the sky is blue? How many say, well, it's probably the reflection of the water. All right, now go to Minnesota. Now go to Kansas. What's the color of the sky in Kansas? Well, it's usually a yellow-green, right? Come on, what is it, gang? It's still blue. Why is the sky blue?
It's absorbing all the red.
Little bit different phenomenon going on here. Let me just tell you about it. It turns out that light coming down from the sun, boom, showers itself upon the atmospheric molecules. Now we got big ones here, we got little ones, we got all sizes up there, okay? And these molecules will scatter off the frequencies of light. It's called scattering. Now, what frequencies will be scattered? Let me give you an example. Let's suppose I have a couple of bells here. Here's a little bell, and here's a big bell. When I disturb these things, they're going to scatter sound off in all directions, and what will the sound be, high pitch or low? Let's try the little one right here. Boom. You hear that? Now let's try the big one. Bing. Did I have that right? No. How many say, no, I got that wrong? Wrong? Okay. No, that's completely wrong. It turns out the little bell will bing, and the big bell, bong. Isn't that true? Guess what behaves the same way up in the sky? The what? Molecule. Molecule. What do you suppose the little tiny, tiny, tiny ones will ring? High frequency or low frequency? High frequency. How about great big ones? Low frequency, okay? Now, what are the size of the molecules in the sky? Large or small? Begin with a S. Small. And then nitrogen and oxygen mostly. Isn't that true? O2, N2. And when that sunlight comes beating down on those things, it scatters off. Light scatters off. And it turns out the color of the sky is the color of all those little bells, or all those little optical tuning forks, or all those little vibrators. And they're vibrating at mostly what frequencies, gang? High frequency. How many know what high frequency looks like to the human eye? Blue. And higher frequency, even violet. Let me tell you something. The sky really scatters off more violet than it does blue. But you know what? We're not so good at seeing violet. We're a lot better at seeing blue. So guess what our eyes tell us the color of the sky is? Begin with a B. You could have done that without the hint. Okay? And it's blue because the tiny, tiny particles are scattering off the high frequency. So we see a blue sky. Okay? Interesting enough? Now, you look straight up at the sun, straight up above. You see the sun white, yellowish white. Okay? Okay, a little bit of filtering coming through, but not very much. How about at sunset, gang? At sunset, when you look at the sun, it ain't white anymore. How many say, well, it's sort of like an orange, but there's probably no reason for that. It's just characteristic of sunsets and sunups to be orange. How many already see why it is that the sun is kind of orange at sunset? Let's take a look. Is the Earth here? Here you are standing right here. Here's the sun at noon. Some of that light comes down, hits the air, scatters off to your eye, and you're seeing what mostly scattered is blue. So you look up and you see blue all around. But when you look directly at the sun, that white light, boom, overwhelms the little bit of scattering going on. You see a white sun, whitish. Okay? So at noontime, boom, you see the sun whitish, huh? How about at sunset? What happens at sunset? Can we do this? We can do this experimentally. I'll tell you what. Let's just do it right here. Here's the atmosphere of the world right here. It's the atmosphere of the world, huh? No, let's do it this way. Here's the atmosphere of the world. And here's the sun. Now the sun. Red, orange, yellow, green, blue, violet. Okay? Bring! What do you guys hear? Well, let me just do it now. I'll do it again. Red, orange, yellow, green, blue, violet. Bring! What do you guys hear? White. Do you hear white? Huh? All the frequencies together give you white. Isn't that true? Right? So you hear what? What color of the sun? Begin with a W. End with ite. Try it. White. All right? Whitish anyway, all right? White sun. All right. Here's our atmosphere down here. The atmosphere. These tuning forks. Blue, 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 violet, violet, blue, blue, red, blue, blue, pink, blue, blue, chartreuse, blue, blue. Get the idea? What's happened? I take and I ring all these. Bring. What do you guys hear? Blue. You all heard blue. That's right. Now there's a little bit of red in there, yeah? A little bit of green in it. Well, mostly what? Blue and violet, yeah? And you heard blue, yeah? Okay. Let's try the sunsets. Can I have a volunteer? Would you stand right here? Put your ear right down here. And I'm going to hit these tuning forks. No, right behind. I want to go right there. I'm going to hit these tuning forks. This is the sun, 150,000 kilometers away, and the sunlight going to come down to the atmosphere, boom, and made her standing on the ground, and here's the sky between her and the sun, yeah? Here we go. We do by experiment. One of the beauties of science is you do by experiment, huh? You don't just do it all in your head. Here we go. Bing! Oh, first of all, I should say this. You guys get the white again. Let me put a reflector here. So all this beam energy goes down here. And this beam energy is going to scatter off here. All right? Okay. Bing! What color do you guys hear? Blue. Blue. Did you hear blue? You all got it? Good. Madro, what color did you hear?
White?
Yeah, she heard white. Why'd she hear the white?
Because she's standing right next to the...
That's right, honey. Some filtering behind her. She got that coming right at her. It's a good thing you didn't have your eyes there. Oh, God, no, no, no. Just get your ear there. Just get your ear, okay? You heard a white, isn't that true? Okay, here we go. Okay, right, like that. Now, we are at sunset, gang. Sunset. All right? Air is thicker. Huh? Bing! What color are you guys here?
Blue.
Yellow.
Paul, would you pass out the Q-tips? Let me remind you, we got blue, 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 red, blue, blue, check with blue, blue, red, blue, blue, pink. All right? Reminder? Huh? All right. Maybe you'll put your ear right behind you. Right behind you. You can even put your eye now, it's all right. Bing! What color are you guys here?
Blue.
Blue. What color are you here, Mador?
Orange.
Yeah, all right. Mador, right here. Right here, right here, honey. Beautiful. Great. You've been a sport. Let's hear it from Mador, all right? All right. Now, let me ask you a question. How come you guys heard blue and she heard orange?
Set up.
Check the neighbor. Check the neighbor. Check the neighbor. How come she heard orange? Hey, is this not neat? Is this not neat? At sunset, of course you're going to see orange. Because at sunset, that light's coming through many, many, many kilometers of air. And what color is being scattered out all along? Blue. Blue is coming. All these people looking up seeing the blue sky. They're seeing the blue that you would have got to you. And by the time that light gets to you, honey, it's all tuckered out in high frequencies. Almost no high frequencies left. And so what finally gets to you, high or low? Low. And so it turns out the atmosphere is transparent to the low frequencies, but not so much to the high. The highs have scattered. And that's why you see the nice colors at sunset. Isn't that neat? It kind of makes sense, doesn't it? Here's another thing that makes sense too. When you look at the clouds, what color are the clouds normally?
White.
They're white. But there's no reason for that. Did you know that?
Yeah.
There's no reason for the clouds being white, is there? Right? Come on, come on. Can anyone see why the clouds are white? If the clouds are white, what do you got to see? Low frequency or high?
Oh.
Oh! But what is gonna? But if the clouds are all little teeny, teeny, teeny particles, they'll only scatter high. So why ain't the clouds blue? My premise was off. I says, if the clouds are all little tiny, tiny, tiny particles, if the clouds, gang, is all tiny, tiny, tiny particles, what are the clouds in fact? How many say, well, in a cloud there's a whole assortment of sizes. Some get so big they absorb and they turn dark, and honey, that's a thundercloud coming up. How many can see that? In the cloud you get all kinds of sizes, yeah? All kinds of sizes, all kinds of scattering, yeah? And all kinds of scattering going to look to you to be what? Hey. Feel good? Yeah. All right. Okay. Any questions?
What about after when the sun sets, instead of red, just before it goes under the horizon, it turns green?
Ah, the green flash. How many people here have seen the famous green flash? 1, 2, 3, 4, 5, 6. How many people saying, what they be talking about green flash, man? The green flash, I have never seen the green flash, okay? The green flash happens when you're looking at the sun, special conditions. You see the sun set, and it's really a kind of a bright reddish, yeah? And all of a sudden, boom, a flash of green, and down she goes. How does that happen? I'm so anxious to see the green flash. But I think it goes something like this. This whole sky here acts like a prism. You know how a prism will put the colors out into the component? You have white light coming in like this, and this fan out, and you get the red and the green and the blue like that with all the colors in between. You know about that? Well, the whole sky acts like a prism. And light will come in like this, boom, like that, and the green will get right to you. Oh, wait a minute. Let me do this again. The prism's higher in the sky. Light coming up from the sun comes in, refracts, and gives you green right in your eye. And the red part's up here. But up here, light's coming in and doing the same thing. The red's like that, and the green is missing you. And the blue, which would ordinarily cut in here and cut that green into bluish green, is just about not there. But down below here, light coming in here does the same type thing. Green like that. Green like that. But red, not bending so much, red comes in and smudges it up. And too bad, honey, right here, the green is overlapped by the red, so what does it look like to the eye? Red and green. Oh, you don't remember that?
Yellow.
Yellow, right, okay. Yellowish anyway, yeah? And so you're not going to be seeing any green. But you only see the green when the sun sets, when it gets way down. You see, like up in here, okay, green hitting. Take this whole thing and move it down. So this part's buried, and you only get the tip. And the green's hitting your eye, and you don't have that red up here coming and smudging because the ground's in the way. I don't have this drawn very well, but you kind of get the idea? When the tip of the prism comes down, you don't have that red from below messing up your green, so you see momentarily a little green flash.
So it'd be like on your frequency diagram, you'd just be seeing the very top of the bulbs.
You're just seeing right here, you're seeing this green. The blues never got you anyway. And the red, usually you're getting the red and the green together. That's what's happening. You're getting the red and the green together. And this thing goes right down at the tip. It cuts off so you don't get the red, and you only get the green, but only for a moment. It's like standing with a thin slit in a prism, getting all these colors. You get red, orange, yellow, green, okay? Now if the slit is wide, you get all smudged, all white, huh? But, if it's very, very wide. But it's a little thin slit will come in and just give you the green, and the red is gone underneath, and it can't mess up your green anymore. And you get that little flash. Watch for it sometimes, gang. It's supposed to be quite interesting. It turns out when I was a kid in school, I remember in the second grade, I was doing some drawings. The art teacher came by, and I was drawing mountains. And I was drawing very distant mountains, and I was making the mountains brown. And I made them brown and sort of green, because mountains have brown dirt and green trees. And the art teacher says to me, "Oh, no, Paul, you don't do that. What you do is you make the mountains bluish." I said, "Bluish?" "Yeah, because they're far away. And far away, dark mountains are going to look bluish." I can't remember if I asked her HC. But I don't know if she would have known the answer. Do you guys know why it is that a dark, dark mountain far away looks bluish to the eye? How many people are familiar with that anyway? Distance. Things in the distance look bluish. How many say, "I've never looked any further than just around my local..." Come on. Okay? And there's another thing, too, you guys don't be knowing about. Distant mountains that are covered with snow that are very, very bright, far away, don't look white. They look kind of yellowish, like some of the blue didn't make it to your eye. I wonder how come distant bright things look yellowish and distant dark things look bluish. In fact, when you look up at the sky, it's all blue. Guess what the background is? The darkness of outer space. The astronauts get up. They're looking down through the same sky. They're looking straight down. Here's the globe right here. Do they see the blue? No, they don't see the blue. What do they see? The color of the earth. We look up, we see blue. They look down and say, "I don't see no blue." They wouldn't say, "I don't see no blue." That means they do see blue, yeah? They see that off at the edge, okay? But what's going on here, gang? Think about these ideas. We'll be talking about them again, okay?